So let's address two issues with the previous video. Okay. Um, you wanted to know why we remove C. Now check the diagram. You realize that when you try to solve it, you can't solve because it's neither series nor parallel, right? So we are trying to, as much as possible, get the system to conform to a series or parallel. You see, we can do either. We can either remove E first, then come and remove C, right? Because they are those which prevent the system from looking more like a series of parallel. There is no hard and fast rule. Okay, so we realize that, from here, if we remove C from the diagram, realize that A can now become in series with D, something like that. Okay, so once we start getting things like that, then we can try and attack that one first. Okay, so it's not like there is any fast and hard rule for removing. No, it's just an observation process and trying to, as much as possible, get a system that would look like a series of parallel. Okay, because once you remove and it doesn't conform, like remember when you remove C, right, you realize that E was making it not to conform, so we had to remove E again. Okay, so it's a step-by-step procedure, and it's just how the nature of the problem is. And the second part is, why do we remove D in the second diagram? Well, it's just has a mathematical basis. You see, D became something like this. D was connected across something like this. Now the numerator is a line, right? So since it's a straight line, the assumption is that then D is a redundant part A, right? So it means that we can remove D. Okay, when you try simplifying, and that's when we remove D. So this time we are just going to consider the minimum cut of this the upper bound and the lower bound. Now when the system gets too complicated, right? This one wasn't so complicated we couldn't solve. So that's why we tried solving. But at a point the system can get so complicated we can't solve. And we will have to just assume the minimum or the lower or upper bound of the system. Okay. So this is how you do it. You first to find the upper bound of the system, right? It is given by 1 minus the product of 1 minus the r part of I. So let me explain that. But before, another concern was, where are these 1 minus r of c's 1 minus r of e's? Well, remember that at a point we assumed that E was not working, or E was working, or C was working, C was not working, right? So depending on where we have assumed, right, when we simplify the diagram, right? So for example, this diagram was assumed that C was not working. So when we simplify the diagram, B and E are in what? Parallel. A and C. So we get R of B multiplying R of what? E for this one. Then A and B are also what? In series. So we get R of A multiplying R of what? D. Right. However, these two are in parallel. So when you put them in parallel, you get what? 1 minus R of B R of E, all times what? 1 minus R of A R of D. Then this whole thing minus 1 minus it. Right. So that's what you see here. So when you check, that's what you see here. Right. So those two are in parallel. But remember, those two are in parallel and in series with F. So we have to multiply by F, and F is here, right? So you can see that we are multiplying by what? F. You can see that we are multiplying by F. Okay. But that was under the assumption that sorry, so we realized that those two are in parallel and in series with what? F, right? So you can say I'm multiplying by F, right? But that was under the assumption that C was not working, and that's why you see the 1 minus C. Okay, yes, and that's why you see 1 minus C. So I think that will solve the issues with the first video. Okay, now let's go back to the original thing we are trying to solve. So we are trying to find for the minimum or the upper bound and the lower bound, right? So the upper bound of the system, like I said, is given by this formula, right? 1 minus the product of 1 minus all the redundant parts. So let's go and see how you find for this R part of I, right? So let's go back to the diagram, the original diagram. This is the original diagram. Now all you have to do is you have to find, when you want to find for the maximum bound, the upper bound, sorry, you have to find all the ways you can get to the output, right? All the ways you can get to the output from the input. So one way you can get is what? You can take A through C, through D, through E, through F. So you can see A, C, E, F. That's one way. The second way you can get is that you can take B through E and F. So you can say B, E, F. That's the second way. Now the third way you can say is what? You can take A through D then F, right? So A, D, F. Is there any other way I've missed? No, I don't think so. So yeah, so this is these three things you can take, right? These three things you can take. So it means that then you can simplify your diagram as you see in this formula, right? But how do you do it in this formula? Well, the formula said that assume that each part is in series, right? But they are connected in parallel with each other. So let's go and see it. So the assumption is you assume that these are all connected in series. So this is connected in series. This is connected in series, right? However, individually they are connected parallel with each other. So when you write an expression for this one in series, you get what? R of A, R of C, R of E, R of F, right? When you write an expression for this, you get R of B, R of E, R of F. When you write an expression for this, you get R of A, R of D, R of what? F, right? When they are connected in series. Now it says that now come and connect these three expressions in parallel, right? To get the upper bound, right? So when you connect these expressions in parallel, I mean, when these expressions are in parallel, it will first 1 minus, then this one will what? 1 minus R of A, R of C, R of E, R of F, multiplying 1 minus R of B, R of E, R of F, times the last one, 1 minus R of what? A, R of D, R of what? F. So then you say, or the minimum reliability of the system will be less than or equal to this bound. Okay, so let's see the expression directly. So that's what you see here, right? So you realize that that's what you see here. So DF, this one and that one, right? Connected in parallel with each other. Then we'll subtract the whole thing from one. Okay, and we are getting the what? Upper bound. The upper bound. Okay. Now to find the lower bound, the formula is also here. It says that just find the product of what? 1 minus the Q cut, right? The Q cut is like the minimum cut of the system. So let's go and see for the Q cut. So for example, your original system was this one, right? So you have to find the minimum cut from this original system, and it's quite the same thing. So check when you check the system, which components are critical, so that when you remove them, the whole system will fail, right? So for example, from the input to the output, right? From the input to the output, for instance, if I remove if I remove A out, right, the system can choose B, right? So if I have to do that, then that means I have to remove A and B, both of them out. So I can say what A and B, right? A and B, if I remove both of them, the whole system will fail. So that's a minimum cut. The second part is I've done for A, right? And let's check B. If I remove B, I mean the system can still go through A. So there's no need to write A and B again, right? So let's check C. Now, if I take C, right, if I remove C, right, the system can go through D or can go through B. But if I remove these three, right, the system will fail, right, because there will not be any way to flow from what the input to the output. So I can say what B, C, D is a minimum cut. Okay. Now, if I consider E, so I've done for C. So if I consider D, right, unless when I remove D, unless I remove C and B as well, right? Or the system will still work. Okay. Or you can also say if I remove D, then I should remove F, right? So you can say D and F. However, you realize that when F alone is also independent, like when you move only F, the whole system will fail. So you don't need a multiple of it. So you can just remove F. Okay. I know it's probably confusing, but the minimum cut is just a procedure. Just consider removing each element. So there is no need to remove D when it has to remove F as well, because if F is what independent as well, and if you remove F independently and it will still work, then there is no need. So you can check for E, and you check that for E, when I remove both E and D, right, then the system will fail. So you can see what D and E, right? And when you remove F alone, the whole system will fail. So that's what gives you the minimum cut. You just consider the elements and see if you remove an element, will the whole system fail or does the system work, right? You can also start from a critical point like F. Realize that when you move F, the whole system will never get to this output, right? So that you will not be confused about whether you should remove a multiple like df, right? Because you know that when you move f, it's already full, so there is no need to add d, and that's what you see, right? So these are the expressions, right? But the formula says that you should find 1 minus the kill cut, right? That's the product. So this is what you do. The kill cut of the system, right, is when the minimum cuts are connected in parallel. Realize that for the series one, we assume that they were connected in series individually, right, but parallel with each other. Here, they were connected in parallel individually. So for example, the reliability of this one will just be 1 minus r of d times 1 minus r of e. That of this one will just be 1 minus r of a times 1 minus r of b. And that of this one will be 1 minus r of b 1 minus r of c times 1 minus what r of d, and that this one um will still be f. That is because you see we are considering these ones individually connected in parallel, right? So if f is connected in parallel and it is only f that is there, to still be f. Okay, now because we are considering individually are connected in parallel, but they'll be in series with each other, right? So it means that these expressions will now come and multiply each other, right? So that's what you see here. So you realize that individually they are connected in parallel with each other. Okay, they are connected in parallel with each other. However, between any two expressions, they are connected in what series. Okay, so that's why you see between any two expressions, they are connected in series. And f will also be connected in series with the whole system. Okay, and that will give you the upper bound. So that basically solves part of your problem when you are working with it. And yeah, you can just ask any question on the page and on the description, and probably I'll do a video to correct that. Thank you.